All right. So the last frame we want to look at is polar frame. And as we discussed before, it is very useful when you have a strong rotational component in your problem that you can use to simplify the equations or use to your advantage. Polar frame, or its three-dimensional extension cylindrical frame, look like this. If you have a motion in arbitrary 3D space, you can define two axes, UR and U theta. This needs a hat. UR and theta on the 2D projection of the motion, and a Z component that says how far up from that 2D plane you are. Now, if you have a force or a net force acting on a particle moving around in space, you can decompose the force along these three cylindrical axes and write the equation of motion. So if you have a force equals mass times acceleration, you can decompose it along the three axes. Sum of forces in radial direction equals mass times acceleration in radial direction. And we saw it was r double dot minus r theta dot squared. Sum of forces in the transverse direction is ma theta. We saw before it is mass times r theta double dot plus 2 r dot theta dot. And the z one was easy. Fz equals mass times az equals mass times z double dot, however much you are moving or accelerating in the z direction. So that is how you can decompose a motion along the three cylindrical axes. And it could be useful if you have lots of information about the rotational aspects. But I want to warn you, there is a little complications with this frame. And often when you want to use this frame is because there is a good rotational component. A good example is when you have, I don't know, a ball being pushed around on a groove using a lever that turns. In this case, you have good information about the rotational aspect of motion. Makes sense to use polar frame. But if you want to find forces, that's where the complication begins. Let me delete one of these lines to make my diagram cleaner. If you want to draw the free body diagram, I'm going to draw it here. But there could be gravity and everything. Maybe the plane is in two-dimensional, maybe not. Really doesn't matter. What I want to emphasize is that, let me change the color of this line. Make it red, the other one blue. The force of the red rod on the ball, if there is no friction, you have this force, normal force from the rod on the ball. And let me actually make this green. So you have this green path. There is also a force from the, let me change it from here, from this groove on the ball that you need to take into account when doing the calculations. Now, here is the complication. What did I do? This N1 by normal forces by definition are normal to the contact surface. So that one is perpendicular. The other one is going to be perpendicular. Is it perpendicular? Almost perpendicular to the tangent line. And that angle is possibly harder to find. So you need to do a lot of geometrical thinking and calculations to be able to properly find the tangent angle, tangent to the curved path, such that you know what the direction of N2, and then you can resolve that. To find that, you can use the information probably in the problem that are given to you to try to find the angle psi. Let me see. This is not a very good diagram, but you can try to find this angle psi. It is the angle from the axis of UR to the tangent in the direction of increasing theta. So if theta is increasing that way, that is the angle psi. Psi you can find. If you know the equation of this path, the green path, r as a function of theta, you can calculate angle psi as not the angle itself, the tangent of that angle psi to be r, which changes, divided by derivative of r with respect to theta. Or this, let's write it this way, f of theta, why green? This is f of theta divided by f prime. No, let me write it as the f of theta over d theta. And that's how you calculate the angle psi. And from there, you know your N2, the other normal force, is perpendicular to the tangent, and you can resolve your geometry. It is going to be a little, sometimes, not always, messy because you have a lot of angles involved. But nonetheless, if you're systematic, you can try to find those. So I think I'll stop here. Now we know how to resolve the equations of motion in rectangular, in normal tangential, and in cylindrical frames. There is just a tiny bit left. I'll cover that in the next video about system of particle. So one more video and we should be good to go.